Welcome back to the Silicon Learners. Today's topic is CDC, means clock domain crossing. First of all, observe this wave. It looks like all the perfect signal B follows signal A and signal A follows the correct behavior. Okay, I show you code also. Here is the code. Okay, you can see here. All looks are perfect, right? But here is the problem. You write a piece of code with a bad, unsynchronized CDC path. You throw it into model sim, you run a functional simulation, and what do you see? Perfect waveforms like this. Okay, and you think everything works flawlessly. Okay, and you think, hey, my logic is fine. Why is everyone panicking about CDC means clock driven crossing? But actually, CDC is the most important part in the VLSI industry, and today we will learn about what is CDC and why does it destroy hardware. Okay, so let us start it. So CDC, okay, as we know, CDC full form is clock domain crossing. Okay, clock, all we know what is clock, but what is domain in the clock domain crossing? So domain means more than one clock. For example, if we have two clock underscore a and clock underscore b, then we have two domain of clock. Okay, so this domain. And another question is, what is crossing? What is meaning of crossing in the clock domain crossing? Meaning of the crossing is the when the two clock are cross each other, means sets the clock edges. At the first edge of clock, the another second edge of clock arises. It is called crossing. So this is about clock domain crossing. Now, why it is bad for the hardware? Okay, so it is a violate setup and hold time. Means if the data changes and arrives at the exact millisecond the receiving blockage age is rising, the receiving flip-flop will get confused. Means the data arrive at the positive edge of clock. At the positive edge of clock, the receiving flip-flop will be get confused, and it causes metastability. What is the metastability? So metastability is the state between 0 and 1. Okay, this is metastability. So between 0 and 1 means the analog state. So it is metastability. Now I will show you clock domain crossing on the actual hardware, physical hardware in the Quartus tool. Okay, so let us go on it. So here is our Verilog code. You can see in the this code we define our inputs and this is all our outputs. We select the two clocks, means we use two clocks in the this code, means two domain. Okay, first is clock underscore a and second is clock underscore b. In the clock domain a, we define our logic when the reset is high, our signal a is 0, and also define when reset is 0, our signal a will be the invert of the previous signal state. Okay, and in the next uh, clock domain b, we define at the positive edge of clock, our if reset signal is high, signal b will be 0, and if it is not 0, our signal b follows the signal a. And as I tell you, you see here in this waveform. Okay, but it is wrong due to CDC effect. And we provide the 100 megahertz of clock in the clock domain A and 70 megahertz of clock in the clock domain B. So now let us see the CDC effect in hardware. For the CDC effect, you have to first of all generate SDC file. SDC file means the, I tell you the full form of the SDC. SDC means synopsis design constraint file. Okay, so first of all you have to make this file in the Quartus tool. Okay, in the SDC file you can see we are assigned the clock A period 10 nanosecond, and we define clock B time period is the 14 nanosecond. Okay, now how we will show this CDC effect. So first I will go on tools menu and open time quest timing analyzer. Okay, in the time quest timing analyzer we will first create timing netlist, then we will read about SDC file. You can see our SDC1.SDC file is so here, and we will update timing netlist. Okay, then we will come at diagnostic tab and the report clock transfer, and here you can see in the first line from clock to clock A. Okay, and at the second column you can see from clock A to clock B. Okay, RR path means rise to rise path, FR path means falls to rise path, RF path means rise to fall path, and as you know FF path is falls to fall path. Okay, now we have to open report for this, so we will go on report timing and click. So here is mathematical proof of timing glitch and clock domain crossing in the time quest analyzer. Okay, so I explain you why it is effect of CDC. Okay, in the you can see data arrival path is 14 nanosecond and the data required path is 14 nanosecond. So it is so relationship means 42 minus 40 is 2 nanosecond. This is the time period between clock signal A and clock signal B. Here you can see from node to node. In the from node A tab pulse A and to node pulse B. Now you can see both nodes are controlled by clock B, but it should pulse B should be launched by the clock B, not the clock A, and this is the why CDC matters. In this code we okay, here is the code. In this code we not synchronize both domain of clock, so that's why this problem occur. Both pulse are drive by the one common clock, so this problem causes by CDC. Okay, and another problems are setup time and hold time also, but the Quartus tool will be forced to idle states. It will give you setups like is 2.891 and you think all is fine in the hardware, but it is not true. For the check actual CDC clock domain crossing, you have to test it on the actual FPGA tool. Okay, so it will give you more idea about the CDC. Now let us discuss on the what are the solution to prevent this CDC. So there is two solution. First is 2FF synchronizer. Means we will synchronize our both clock domains. And the second is required and acknowledge handshake. Now I will explain when you will use this both solution. Okay, in the two flip-flop synchronizer, as I tell you, there is two flip-flop 1 and flip-flop 2. The task of the flip-flop 1 is the catch unstable state and a spinning signal crossing over from the old domain. Okay, it might go metastable and start hovering. Now task of the flip-flop 2 is the sample that unstable value at the next edge of clock. So this is the task of the flip-flop 2. Now when it will sample that unstable value, so it will sample it when the unstable state will be become a stable state. Okay, so that's how this 2FF synchronized solution works. Okay, the another solution is the required handshake protocol. Before we are going that solution, first discuss the drawback of the two flip-flop synchronize. Okay, drawbacks. So first drawback is pulse width degradation. In the pulse width degradation problem, if a fast clock domain sends a quick one cycle data pulse, a slower clock domain might completely miss it. So this problem. First domain is fast and second domain is slow. The data lost can be happen in the hardware. Another problem is multi-bit vector chaos. If you try to pass a multi-bit command bus like changing state code from 00 to 11 through individual two flip-flop synchronizer, the routing delays to those registers will differ slightly. Means two flip-flop synchronized solution only for 1 bit data path. It is give unstable value or data loss in the when the multi-bit data, or there is a race condition also can be occur. Okay, now the go on required and acknowledge handshake protocol. The required means REQ and acknowledge means ACK. Okay, there is four-step architecture of the required and acknowledge protocol. The first step is this. First step is the required goes to high. Okay, the second path is this. So first of all, in the required and acknowledge architecture, there is two domain. First is sender domain and second is receiver domain. Now there is four step. First, at the sender domain, required goes high. At the receiver domain will be sees required is high. So it will grab the data and it will set acknowledge high. But when it will show required goes high. Okay, now at the third step, in the third step at the sender domain, it will see the acknowledge and it will drop the required to low. Means at the sender domain, when it show the acknowledge high, at the receiver domain it will goes to low. It is force to go, required goes to low. Okay, and at the fourth step, here is third. At the fourth step, at the receiver domain, you will see a required go to low. Receiver domain will see required is go to low, and it will also drop the acknowledge low. So this is the fourth step of the required and acknowledge protocol. Again I explain it. So at the sender domain required goes high first, and at the receiver domain when receiver domain C required is at 1, it will grab data and set the acknowledge at high. Now at the sender domain will see acknowledge is high and it will drop required to low, and at the other side receiver domain will see it that required is the low and it will force to acknowledge also goes to the low. In the next video we will understand about the solutions on the hardware, means how we can implement this solution on the actual hardware means on the our Quartus tool. So why CDC is critical in VLSI industry? It is causes the chief failures and impossible to debug in the lab. It causes metastability. That's why it is the critical in the VLSI industry. According to the industry data, 40% of ASIC respawns are due to CDC bugs. Okay, means you can understand in that way 40% loss causes due to CDC bugs, and average debug time for this CDC problems are the 3 to 6 months. So that's why CDC is the most important topic in the VLSI industry and also in the interview questions. So thank you for the watching. In the next video, as I said, we will implement solution on the our hardware of the CDC, how to prevent CDC, and we will cover this question how we can implement 100 megahertz to 300 megahertz pulse crossing on the hardware. Okay, thank you for the watching.